Okay, thank you very much for giving me this opportunity. I've been here several times, part of the program, some of the meetings, and actually I'm very impressed. I think this program, the program of the summer schools and the meetings around it, that initiated actually by Chita Chong, and of course with the essential help of you and Ted, I think it's very remarkable. I don't think there is any other program that goes so regularly for such a long time with such a varied set of participants. What I hope is that the program will continue on for many more years to come. Okay, so we are going to talk a little bit about singular cardinal combinatorics, and we talk about properties of cardinals like Aleph Omega square, and so on. And they look rather similar. Both of them are singular cardinals of cofinality omega, relatively small. There shouldn't be much of a difference, but as we shall see, there are actually very substantial differences between these cardinals. By the way, we're mostly going, in order to make the titles shorter, I put it Aleph Omega and Aleph Omega square. It's actually, I'm going to talk about the successors. It's Aleph Omega plus 1 and Aleph Omega square plus 1. But it, of course, connects the properties of the successor from the properties of the cardinal itself. So we consider properties of large cardinals which potentially can hold for small cardinals. And typically, you're talking about compactness or reflection properties, which automatically holds for cardinals like weakly compact, strongly compact, super compact. A compactness property is a property that usually you got a mathematical structure, and you say that every small substructure is the property. A compactness phenomena is the fact that you can infer that it holds for the whole structure. Reflection property is exactly the dual. It says that suppose that the big structure is the property, then there is a small substructure with the property. Now, of course, they are essentially the same property. One is dual to the other. Reflection, a compactness property exactly corresponds to reflection property for the negation of the property. So they come in pairs. Okay, so for example, properties of a regular cardinal, we can talk about the tree property. Every kappa tree is a tree with, here is kappa many levels. Each level of cardinality less than kappa, and the kappa tree property says there exists a branch of length kappa. Stationary set reflection. Suppose you have a set S which is stationary in kappa, then you can find some initial segment such that S is stationary in that initial segment. Here is kappa, here is S, and you can reflect the fact that S is stationary to some smaller ordinal or cardinal. A variation of this principle is when we make some assumption about a stationary set, like the cofinality of its point, and maybe other assumptions. A typical case is when we consider a stationary set where the points have fixed cofinality like omega. Now, what we might call weak chunk conjecture, it's the you have a structure, let's say, with universe kappa, and in a countable language, and you got a distinguished unary predicate, R, which has got cardinality less than kappa. Then you want to reflect the fact that it is a structure where the size of this distinguished predicate is less than the size of the structure. So you want an elementary substructure which has got smaller cardinality, but also you reflect the fact that, there is a typo, it should be less than the cardinality of B. Then we want to reflect the fact that this distinguished predicate has got smaller cardinality. Now, the reason I put it like that is because you put condition on the cardinality of B. Now, the real Chang conjecture, usually you talk about pairs of cardinals, and you talk to the pair kappa lambda, arrows kappa prime, lambda prime. If for every structure which domain is kappa and distinguished predicate lambda, as elementary substructure that the cardinality of B is kappa plus, kappa prime, and B intersect lambda has got cardinality lambda prime. And she's mainly interested in Chang conjecture for the form of successor cardinals, kappa plus kappa, arrows, lambda plus lambda. Note, by the way, that note that if you talk about the case of let's say Aleph alpha plus 1, where alpha is countable, then if it satisfies the weak Chang conjecture, then automatically you get some beta such that Aleph alpha plus 1, Aleph alpha, arrows, Aleph beta plus 1, Aleph beta. The reason is very simple, because alpha is countable. If for every beta less than alpha you have a counterexample, you can merge these counterexamples, and then the weak Chang conjecture will give you a contradiction. So this is one option. Now another. By the way, I'm picking properties that were considered, people did study. I mean, that's not something that I invented specifically for this talk. Now, existence of transversal. Suppose you have a family of countable sets, which has got cardinality kappa, and suppose that every subfamily, again typo, of a smaller cardinality as a transversal, a one-to-one choice function. Namely, if you take a small subfamily, you can pick a point from each member in a one-to-one way. And then you want to infer that the same thing holds for the whole family. So this is a compactness properties which is interested. Now another property is compactness of freeness of groups. Suppose that G is either abelian group or non-abelian group. It's got cardinality kappa, and suppose that every subgroup of smaller cardinality is free, then G is a free group. For abelian, that means free. It means that you can write G free. That means that G can be written as a sum of a certain number of copies of the integers. And these are the nicest abelian groups you can have. And the issue is if every small subgroup is nice, you want the whole group to be nice. Okay, now a topological example. You got the notion of a topological space being a collection-wise Hausdorff. Collection-wise Hausdorff means that you got a discrete in the space, here is the space X, you got a discrete set of points. No point is a limit point of except of course the point themselves of the set. And you want to separate it. Collection-wise Hausdorff means that you can separate it. You can find open sets around each of the points which are mutually disjoint. This is, for instance, a necessary condition for the space being metric. And now suppose that here is the statement is there. If Y is a discrete subspace of X, then there is a mutually disjoint family of open sets, which for each individual members of Y, it's got its own open set, such that they separate this whole thing. And suppose that X is topological space of cardinality kappa, so that every subspace of cardinality less than kappa is collection-wise Hausdorff. Is X necessarily collection-wise Hausdorff? In order to avoid the trivial counterexamples, we usually have to assume some local smallness condition about X. For instance, there are several about the size of neighborhood base and so on, but let's, for the sake of this talk, let's say that X is locally small if every point has got a neighborhood which is relatively small, of cardinality less than kappa. Now, if a cardinal kappa is weakly compact, the usual definition of weakly compact, then it has all the above properties. It has got all the properties that we listed above. Now, if V equal L, then each of the above compactness properties actually characterize L being weakly compact. Namely, in L, that is the only cardinals that can have this compactness property, except for the weak Chang conjecture. The weak Chang conjecture, the way I phrased it, is actually true for the weak Chang's conjecture is true for every inaccessible, trivially, okay, now the question, which is, I think, a central question for many of us in combinatorial set theory, is to what extent these properties of large cardinal can consistently hold for small, relatively small cardinals. So this is, to what extent it's really unique to the large cardinal, or you can have small cardinals with the same properties. Another question is which combinations of this compactness property can hold at a small cardinal. To what extent the small cardinal can look like the big inaccessible cardinal. What is the consistency strength of having the small cardinal satisfying this property? Now, is the compactness property survives small forcing extensions? You see, one feature of the large cardinal axiom is the fact that if you do forcing extension of size less than that cardinal, then it remains, it preserves this property. That's almost it's almost a definition, right, of the concept of a large cardinal axiom. Okay, in this talk, we'll mainly be interested in successor of singular cardinals. So particularly Aleph Omega plus 1 is the first successor of singular cardinals, and this will be of my main interest. Okay, so now there is one of these properties, or a failure of one of these properties is something which is disastrous for any kind of compactness. And that's the stationary set reflection. Namely, suppose that you got a regular cardinal kappa. And you have a stationary set, subset of kappa, such that every point is a cofinality omega. And it is non-reflecting. No initial segment is stationary, but the whole set is stationary. Then essentially you can find counterexamples to almost all of the properties I listed and many, many more. There is a family of countable sets of cardinality kappa such that every smaller cardinality subfamily, you can have a one-to-one choice function. But you fail to have it for the whole family. There is a group with cardinality kappa such that every subgroup is free, but G is not free. There is a topological space which is locally countable, and every point has got a countable neighborhood, so that every subspace of smaller cardinality is collectionized Hausdorff, but the space is not collectionized Hausdorff. And so on. You can essentially, almost every compactness properties you can think about will fail once you have a non-reflecting stationary set of points of cofinality omega. There are two things which are problematic in what I said right now, which is the Chang's conjecture and the tree property. And maybe we'll have time to say something about it later. But if you take a stronger anti-compactness property, which is the combinatorial principle square, suppose that kappa is a successor and square lambda holds, then kappa fails to have any of the compactness property listed above. I will not define square, but it's some kind of combinatorial principle which holds in L everywhere. And what about the ultimate L? Does it hold there? Anyway, this is the super anti-compactness property. Namely, once it holds, then it fails to have any of the properties above. So, in particular, it has an implication for the consistency strength of having the compactness property. Namely, suppose you got a kappa which is successor of a singular cardinal, kappa equal lambda plus when lambda is singular. If you have the compactness properties, then that means that the square fail. But the consistency strength of a square fail at a singular cardinal should be rather strong. Exactly what it is, a subcompact but it should be generally a rather large cardinal in order to have the compactness properties at a successor of singular. Okay, so now we say that we are interested in Aleph Omega, and the point is or Aleph Omega plus 1, to what extent it could be compact cardinal in that sense, satisfy these compactness properties. Okay, so let's start with few good news. What is consistent? How compact can Aleph Omega plus 1 be? It is consistent, assuming the consistency of omega many supercompacts, that every stationary subset of Aleph Omega plus 1 reflects. Okay. So that's one consistency option. Now, it is consistent for some large cardinals, the Chang conjecture, Aleph Omega plus 1, Aleph Omega, double arrows, arrows Aleph 1, Aleph 0. Namely, if you got a structure on Aleph Omega plus 1, you have a structure of the form Aleph Omega plus 1, Aleph Omega, blah, blah, some other relations, then there exists elementary substructure B, such that the size of B is Aleph 1, and B intersect Aleph Omega is Aleph 0. Now, the original proof of Levinsky, myself, and Sherlock uses some large cardinal roughly around huge cardinals. ℵω2 got the results from just one supercompact. That's a relatively recent result. We'll say something about the proof later. Okay, what about the tree property? Again, a result with Sherlock quite a number of years ago. It is consistent by assuming the consistency, again, of some large cardinals around huge cardinals, that Aleph Omega plus 1 is the tree property. Neyman and Sinapova version uses only omega many supercompacts. And by the way, the proof is amazingly simple. I mean, the construction of the model is amazingly simple. What you do, and there is a very interesting feature there. Here are here is the omega sequence of the supercompacts. Kappa n's. Here is kappa omega, which is the supremum of the kappa n for n less than omega. So the cardinal that will become Aleph Omega plus 1 will be kappa omega plus. And the way you get it to be Aleph Omega plus 1, you simply collapse cardinals here. But you collapse it, the usual Levy collapse. But there is one interesting feature. You pick a cardinal row here, which you cannot name it a priori. This is something that you just, it's an existence proof. There exists a cardinal row, a singular of cofinality omega, such that you do the following collapse. You collapse everything here to omega. You keep rho plus, and you collapse everything here to cardinality rho plus. And then you do the Levy collapse in the next of the intervals. So it's simply a product of Levy collapses. That's the model. So the model is not very complicated to construct the model. I mean, there is the issue of proving that it has the tree property there. And the point is that this row, the one below kappa 0, that you pick to become Aleph 1, you pick it, you don't know a priori which cardinal. You just prove that there exists something like that, such that this forcing will get you the tree property. And this row is something that, in some sense, looks very much like kappa omega. It's something that in some sense it's something which reflects kappa omega. And that reflection actually will cause us problems if you want to extend some of these results. By the way, the ℵω2 proof for the Chang conjecture is exactly the same. Not exactly the same, but you take one supercompact for getting the Chang conjecture, and then you look at this omega plus 1 successor, and then you show that there exists some row like that if you collapse rho to omega, keep its successor, and collapse kappa 0 to this interval, then Chang conjecture will be. Sorry? No, you can take product. You can take a product, yeah. Okay. Now, what about the thing about topological space being collectionized Hausdorff? Then Sherlock proved that assuming the consistency of supercompact cardinal, it is consistent that every topological space of cardinality Aleph Omega plus 1, which is locally countable, note that thing, if every subspace of smaller cardinality is collectionized Hausdorff, then the space is collectionized Hausdorff. So these are things that Aleph Omega plus 1 can be compact for several of the properties. Well, not for all of them, unfortunately. These are the bad news. A result of result with Sherlock showed there is, for instance, the existence of transversal, Aleph Omega plus 1 cannot be compact for existence of transversal. There exists a ZFC counterexample. There exists a family of countable sets of cardinality Aleph Omega plus 1, so that every smaller cardinality subfamily has transversal, but the whole family fails to have a transversal. This is something which is a ZFC. This is something which Aleph Omega plus 1 can never be compact for this property. Freeness of group. There is an abelian group, for instance, such that every smaller cardinality subgroup is free, abelian group of cardinality Aleph Omega plus 1, but the whole group is not free. Collectionalized Hausdorff. Remember that the result of Sherlock by a space which is locally countable. Suppose you give up the local countable. You say locally of size Aleph 1. Now you are in trouble. Aleph Omega plus 1 cannot be compact for that. There exists a topological space of cardinality Aleph Omega plus 1, which is locally of cardinality at most Aleph 1. Every smaller cardinality subspace is collectionalized Hausdorff, but the whole space is not collectionalized Hausdorff. So these are things which Aleph Omega plus 1, as a theorem of ZFC, fails to have compactness. They are, and by the way, these are all prototypes of prototypical examples of many other reflection properties. And by the way, the same is true for Aleph Omega times n plus 1 for n less than omega. Okay, so now, just a minute. Okay, so now suppose you try to combine, consider a reflection principle. You try to combine the Chang conjecture with stationary reflection. Namely, suppose you have a cardinal successor of singular, let's say. We say the delta reflection holds at a typo, holds at lambda, denoted by delta of lambda. If every structure such that S is stationary subset, you can get elementary substructure that is a witness to the weak Chang conjecture, namely its intersection with I'm so sorry. Okay, let me state it like that. It's this is I wrote after a very bad jet lag. So okay, so here is the combination of Chang conjecture and stationary reflection. Okay, so suppose you have the following picture. Here is the cardinal, I'll denote it lambda plus. You have some stationary subset of lambda plus. This is stationary. You have some distinguished predicate, R0, and some other predicates. What you want, the reflection you are asking for, is elementary substructure B with the following property. One, of course, that B has got cardinality less than lambda. You reflect below lambda. Two, that B intersect R0 has got cardinality less than the cardinality of B. And three, that's where the stationary reflection comes. If you look at S intersect B, those points in S that happen to be in B, this is stationary in sup B. Namely, you want to have something which is like a Chang structure, and now, the nice thing about this reflection property, that it's preserved under forcing of size less than lambda. You can easily check that. Okay, so now suppose that you got a successor of singular cardinal and this property holds. Then trivially satisfies stationary reflection, definitely satisfies weak Chang conjecture, that follows from the definition. But also, all the compactness properties we listed before, except one, you have it. For instance, you've got a family of cardinality kappa made up of sets whose cardinality is bounded below lambda. If every subfamily of smaller cardinality is a transversal, then F is a transversal. If G is an abelian group such that every subgroup of smaller cardinality is free, then G is free. If you got a topological space which is locally of cardinality delta, delta is a bound below lambda, then X is collection-wise Hausdorff if every smaller subspace is collection-wise Hausdorff and X is collection-wise Hausdorff. Well, we got all the properties I listed before. We didn't list the tree property, and for good reason, because the result with Laura Fontanella shows that it does not imply the tree property at lambda plus. Almost. We'll talk about it. Now, this principle, assuming the consistency of omega many supercompacts, it is consistent that this delta reflection principle holds at Aleph Omega square. Remember, at Aleph Omega, it cannot hold because it implies reflection and compactness properties which Aleph Omega, as a theorem of ZFC, fails to have. So in the resulting model, Aleph Omega square plus 1 is compact for all the properties considered, except possibly for the tree property. Well, if you want the tree property, you can manipulate the proof a little bit, again with Laura, that you can arrange to have this reflection principle, this delta reflection principle, together with the tree property. So in the resulting model, Aleph Omega square plus 1 has all the compactness property we considered and many more. So you see there is a difference here between Aleph Omega and Aleph Omega plus 1. Namely, Aleph Omega can be compact for some properties, but fail to be property for other properties. Aleph Omega square looks much more like a large cardinal in that sense. It consistently can be much more compact than Aleph Omega square plus 1, more than Aleph Omega plus 1. That's what I said before. A slight modification of the above construction gets a model in which this reflection principle holds, but Aleph Omega square plus 1 fails the tree property. So unfortunately, this reflection principle, which the delta, which I wanted to have, kind of something which covers as much as possible, that doesn't cover the tree property. So now let's try and see some more finer analysis. What's the difference? Where does the difference between Aleph Omega square plus 1 and Aleph Omega lies? And here we need to have some facts from what's known as the theory of possible cofinalities from PCF theory. Okay, so suppose you have a singular cardinal, and mu is its cofinality. A lambda plus scale is a sequence of regular cardinals less than lambda, cofinal in lambda, and a sequence of functions in the product of these kappa i's, which is increasing and cofinal in the product, where the partial order is that you are eventually above, one function is above the other. Okay, so what is a lambda plus scale? So lambda plus scale, you look at lambda, and you say lambda is the sup of the kappa I for I less than cofinality of lambda. These are regular cardinals. Now you consider the product of the kappa i's, functions in the product of kappa I, and you say that f is less or equal g if for almost all I less than cofinality of lambda, f of I is less or equal than g of I. Namely, if g bounds f almost everywhere. Almost everywhere means a tail. Now, lambda plus scale, that means a sequence g alpha for alpha less than lambda plus of functions in the of lambda plus of functions in this product, which is increasing. Namely, if alpha less than beta, then g of alpha is less or equal g of beta in this partial order, and it's cofinal. Cofinal, that means that for every h in the product of kappa I, there exists some alpha such that g alpha bounds h. Now, okay, now a theorem of Sherlock tells us, I think it's a remarkable theorem, that for every singular cardinal lambda, there exists a lambda plus scale. Note that it doesn't depend on any cardinal arithmetic. Doesn't matter what the size of this product of the kappa i's is. You can always find a sequence of kappa i's such that their product, in that sense, has got a cofinal sequence of length lambda plus. That's something which is always true. So that's a lambda plus scale. So now we have to say something which plays a role in the combinatorics of the singular cardinal, the good points and bad points. So suppose that lambda is singular, and you got a scale, a lambda plus scale. Now a subset, you got a subset of the scale, of D, a subset of the G alpha for alpha less than lambda plus. Typically it will be a bounded subset. You say that G is disjointifiable if you can find tails, if for every alpha less, you can find some function. D is made up of some of the functions here. You can disjointify D if you can, for each of these functions, you can find some initial segment, namely eliminate, you cut off some initial segment of each of the function in D, so then what's left, these functions are strictly increasing. Namely, for every alpha less than beta, and once you are above this initial segment that you cut off, the D alpha and the D beta, then G alpha I is less than G beta I. I mean, the functions can be a little bit messing around, but eventually each one is above the others, and you can make it in kind of more uniform way, namely for each one of them eliminate initial segments such that now on what's left, they are strictly increasing according to the indices. So that is disjointifiable. Now, a point in the scale is said to be good point of the scale if there is a D, again typo, I apologize, there exists a D which is cofinal in alpha, which is disjointifiable. So a good point is a point in the scale that you can find an unbounded set of indices that you can disjointify. That's a good point. Note that if alpha good and the cofinality is bigger than alpha, then the set of beta which are good for G contains a closed unbounded subset of alpha. Why is that? For a very simple reason. If you got a cofinal set which is disjointifiable, then every limit point of that disjointifiable set is every initial segment of that disjointifiable set is a disjointifiable set. So every beta which is a limit point of this thing is itself. So the good points, in some sense, state in their own thing. I mean, if a point is good, it makes sure that it's, so to say, friends. A club of points below it are also good. Okay, and a scale is good if for most alphas less than lambda plus are good. Namely, a closed unbounded subset of lambda plus are good. Now, we call them good. This is a term that introduced by Sherlock. But actually they are bad. They are bad for compactness. And by the way, it's not, in some sense, it's not too surprising, because you see, in some sense, if you think about the good scale, it by itself is a counterexample to compactness. Because good scale, that means that for every alpha, or most alpha, you got cofinal sequence which is disjointifiable. Namely, for every initial segment you can find, you cannot find it, you definitely cannot find it for the whole sequence. You cannot find it for the whole sequence because the functions belong to a product of small of cardinal lambda plus. Suppose you have a D which is a subset of lambda plus, D cofinal, then D is not disjointifiable. Why is that? Because suppose you can disjointify, you can eliminate some initial segment, and what's left you are increasing. Now, in what's left, because D is cofinal in lambda plus, there exists one point which survives for unboundedly many of them. But suppose that the point is I. But these are elements of kappa I, which should be increasing. But kappa I is smaller than lambda plus. You can't have increasing sequence of length lambda plus in smaller cardinal, kappa I. So by itself, a good scale is a counterexample to compactness in that sense. But anyway, it's something that's able to generate a lot of the counterexample to compactness that we have. The weak chunk conjecture fails for lambda plus. If you have a family of countable sets, every subfamily of well, I put the theorem, assume the cofinality of lambda is omega. There are versions for the cofinality is bigger than omega, then the set of a counterexample to transversal would not be countable, it will be of cardinality, cofinality of lambda. There is an abelian group of cardinality lambda plus such that every smaller cardinality subgroup is free, but G is not free. Here we use the fact that cofinality is omega. Every topological space with local F cardinality at most Aleph1, if every smaller cardinality subspace is collectionized Hausdorff, but X2 fails to be collectionized Hausdorff. So having a good scale is bad for compactness, generates counterexample to compactness. Okay, so now, actually I think that, or maybe I'll say it. Suppose you got, and actually you could do a finer analysis of this thing, talking about what is the cofinality of the points which are not, suppose you got a scale which is not good, what are the cofinality of the points which are not good? I'll skip that. Actually, I want to skip that. Okay, so now comes the thing about Aleph Omega plus 1, which makes Aleph Omega plus 1 rather special. Suppose you have an Aleph Omega plus 1 scale. Doesn't matter what the cardinal arithmetic is. Then for every alpha, which is with cofinality is at most Aleph 4, then it's automatically good. Namely, those which are large enough cofinality are automatically good. Where does Aleph 4 comes from? It's exactly the same proof that goes into Sherlock bound for the, for 2 to the Aleph Omega, where Aleph Omega strong limit is less than Aleph Omega 4. It's exactly the same analysis that gets you Aleph 4, gets you the analysis here, and the fact that this point are good. That means that, for instance, for n at least 3, the chunk, remember we had the chunk conjecture, we mentioned the results of originally the one with Sherlock and Levinsky, but the better result of ℵω2. The chunk conjecture, Aleph Omega plus 1, Aleph Omega, if you think about Aleph n plus 1, Aleph n, if n is greater than 3, that fails. That automatically fails. It cannot be true. Why is that? Well, you just use this fact. Namely, take your structure A to be essentially something which codes, this is Aleph Omega plus 1, and something which essentially code the scale. Less than Aleph Omega plus 1. This is the Aleph Omega plus 1 scale. And let's say Aleph Omega here. And blah, 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 some other set theoretical thing. Now, suppose that you have a B, which is an elementary substructure, whose cardinality of B is Aleph n plus 1, and B intersect Aleph Omega, the cardinality is less or equal Aleph n plus 1, but in that case, if you're throwing enough set theory, it must be exactly the previous cardinal. It must be exactly Aleph n. Then the order type of B must be exactly Aleph n plus 1. The order type of B must be exactly Aleph n plus 1. But now you know that the point, look at sup B. Sup B would have cofinality Aleph n plus 1. Because n is at least 3, that means that the point is good for the scale. So there exists a D, let's call this gamma. There exists D gamma, cofinal in gamma, such that D can be disjointified. D does not have to be included in B. But the fact is, so here is the picture. Here is gamma. Here are some points. Here are some points in the elementary substructure B. Note, by the way, that if alpha if an ordinal alpha belongs to B, because it's elementary substructure, then G of alpha is included. The elementary substructure knows about the scale, it knows about G alpha, the alpha member of the scale, is included in B. And included in B intersect Aleph Omega, really. So the number of possible values of each G alpha is relatively small. It's relatively, it's at most Aleph n. But now you have this cofinal set which can be disjointified. You have this, it's somewhere here, this disjointifiable set. Disjointify them. And somehow they fit between the functions that that the elementary substructure knows about. But what will happen is that there will be a point where you should have too many values on the members of the scale that B knows about. So that shows that Chang conjecture of this type fails. And by the way, it's a very interesting problem. So what did we get for Chang conjecture for Aleph Omega plus 1? We know that it is consistent, modulo the large cardinals, but namely we can have Aleph 1, Aleph 0. Cannot have, this is already impossible, Aleph 4, Aleph 3. Well, still there is possibility. What about Aleph 2, Aleph 1, or Aleph 3, Aleph 2? That's open. It's very, very likely that you cannot have that as well. If you look at the proof of the consistency of the Chang conjecture, you look at this proof, there is always this, the thing that I mentioned of the very judicious choice of what would be Aleph 1. And you pick an Aleph 1 which, it will be very difficult to make a choice like that if you want to have it for Aleph 2 of Aleph 3. So there is a genuine difficulty in this case, and it connects with the problem which James defines as his favorite problem, whether you could have, suppose you start with any model of set theory. Could you force, in such a way, do some forcing extension, whatever forcing extension you want, in such a way that Aleph Omega plus 1 becomes, let's say, Aleph 2 or Aleph 3. And that's open. But if you have Chang conjecture and you have a wooden cardinal on top, you can use a wooden tower construction to make Aleph Omega plus 1 into Aleph 2 or into Aleph 3. So that's an interesting open problem. But anyway, note one thing, that for Aleph Omega square, we can have Chang conjecture in some sense because of the delta reflection unboundedly many below. Okay, so now another thing. It's not a corollary, it's a theorem of Sherlock that tells you that every stationary subset of Aleph Omega, if you got a reflection for every stationary subset of Aleph Omega plus 1, then every scale is good. Actually, we have the argument for Sherlock. We have all the ingredients. Remember, we know that every point of cofinality omega 4 is good. Suppose you have stationarily many points which are not good. The cofinality of that point must be the cofinality of that point must be either Aleph 1, Aleph 2, or Aleph 3. And now you say, okay, suppose that set reflects. Maybe it reflects to set of points of cofinality Aleph 3, for instance. But then this set, if every stationary set reflects, this should reflect to any points of cofinality Aleph 4. That point is good. We say that if a point is good, it contains a club of points which are good. That immediately gets you contradiction. And therefore, if every stationary set reflects, then Aleph Omega plus 1 scale is good. Think about the implication of that. Stationary set reflection is a compactness property. Chang conjecture is a compactness property or reflection property. Having good scale is an anti-reflection property. That means that you cannot have simultaneously you know that the reflection property of stationary set reflecting implies the anti-reflection property of a good scale. Or chunk conjecture is incompatible with every stationary set reflect. This is exactly what he say. Chunk conjecture for any kind of chunk conjecture for Aleph Omega plus 1 is incompatible with stationary set reflection for Aleph Omega plus 1. Okay, so now something about the tree property, and here it's something which what I'm going to talk about is really mainly problems and results which do not separate. I mean, the title of this slide is misleading, which do not separate. We don't know yet whether it separates Aleph Omega plus 1, Aleph Omega squared plus 1, but there's some indication that that might be the case. As you said in the talk, if we can't prove it, let's prove something, let's make a conjecture. And the conjecture is that there is, even for the tree property, there are some substantial difference between Aleph Omega plus 1 and Aleph Omega squared plus 1. Now, in all the models in which Aleph Omega plus 1 is the tree property, no scale is good. There is something about the proofs that no scale is good. Roughly, if you remember my outline of the proof of the Ne'eman-Sinapova proof, you say, okay, you're taking still on the board? Yeah, no. You look at the sequence of the supercompacts, and then you make a choice of some rho, which is cofinality omega, which is reflects kappa omega plus to many respects. And then you collapse rho to omega, you collapse everything here to rho plus, and collapse the thing between the cardinals, you do a simple Levy collapse. The choice of this rho is not something that you can specify beforehand. It's something that you can choose it. There is a large set in some measure of choices of this particular rho. This rho reflects whatever happens at kappa omega plus. Now, kappa omega plus is, you are above a supercompact. Now, it's quite easy to show that above a supercompact, no scale is good. By the way, that's not surprising. Remember, a good scale is anti-compactness property. Supercompact is, like the name indicates, the supercompactness properties. So no scale, the singular cardinal of small cofinality above the supercompact is good. All scales are bad. If that rho somehow reflects whatever happens upstairs, if you make it into Aleph 1, what it translates, the scale is still a scale. The scale that you have here, because the forcing is relatively nice. Remember, the scale is made up of functions of length omega. This part of the forcing does not change, does not introduce any omega sequence. It's closed. This part is small enough, so the scale is really a scale. So the scale is bad. It's still a bad scale. The fact that this becomes Aleph 1 immediately generates a stationary set of points of cofinality Aleph 1, which is bad. So there is something that looks like inherently in the proof, which gets you the bad scale. Now, but now note the following thing. A theorem of Sherlock tells you that suppose you got a cardinal lambda, singular cardinal, which violates the singular cardinal hypothesis. Namely, for instance, suppose that 2 to the cofinality of lambda is less than lambda, but lambda to cofinality lambda jumps above lambda plus. Then automatically there is a good lambda plus scale. So in some sense, a failure of singular cardinal hypothesis is anti-compactness properties. Now compare that with the proof, with now classical proof of Solovay that tells you that above a strongly compact, the singular cardinal hypothesis is true. Namely, if you got compactness, automatically that implies the singular cardinal hypothesis. Failure of the singular cardinal hypothesis gives you an anti-compactness property, which is the existence of good scale. So now let's see what can we say about the thing with. So now the question is, is the tree property at successor of singular consistent with the failure of the singular cardinal hypothesis? Now, many years ago, I dared to conjecture that it's impossible, that the tree property is inconsistent with the successor of singular with that singular cardinal violating the singular cardinal hypothesis. Can I quote you that you supported this conjecture? That you support?
Yeah, I stated it's a problem.
Sorry. Anyway, I was bold enough to put. Sorry. Well, cautiousness was actually verified because of the result of ℵω2, the consistency of omega many supercompacts. There is a preliminary result, an important result of Neyman, that tells you that there exists, using again omega many supercompacts, you can have a singular cardinal violating the singular cardinal hypothesis, having the successor having the tree property. ℵω2 got it down to Aleph Omega square. Now, since Aleph Omega square in this model, of course, violates the singular cardinal hypothesis, there exists a good scale. So that means that you can have the tree property and having good scale. So these two things, this reflection property and the anti-reflection property, can live together. Still, I dare to conjecture that for Aleph Omega plus 1, my previous conjecture holds. Namely, even in a stronger sense, that if it has the tree property, then no Aleph Omega plus 1 scale is good. In particular, that assuming that Aleph Omega plus 1 is the tree property, then it satisfies the singular cardinal hypothesis, because failure of singular cardinal hypothesis gets you a good scale, and it fails stationary reflection, because stationary reflection. So now it immediately raises problems. Could you get a model in which Aleph Omega plus 1 is the tree property and you have full stationary set reflection? Could you have a good scale in the tree property? I suspect not. Again, somehow, because maybe you are too hooked on the existing proofs of the tree property at Aleph Omega plus 1, that in some sense, it seems like the bed scale is inherent in some sense in the construction of the model. Now compare that with the fact that look at Aleph Omega square. Aleph Omega square, the tree property, this is the result with Fontanella, it's consistent with the delta reflection. So the delta reflection implies stationary reflection. So you got stationary reflection there, the tree property is true. There is no, there is no good scale, that's not too surprising. Okay, by the way, the reason that the connection, why did I make the conjecture about the good scale and the tree property? Because you see, what happens is, in some sense, here is here you have the scale, the lambda plus scale. And now, what does it mean that the scale is good? The scale is good means that you can find some cofinal set for each alpha, you can find a cofinal set which can be disjointified. Now, in some sense, you can think about the following problem. Could you take you know that you cannot fit together these disjointifying sets. You cannot find a branch, so to say, disjointifying set that will work all the way up to lambda plus. This is the argument we had before, that lambda plus, the scale cannot be, you cannot have cofinal set in lambda plus which can be disjointified. So it looks like almost it gives you a tree with no branch. The problem is that the tree is too wide. If you look at all possible cofinal set, the tree is too wide, so it doesn't give you immediately. But the attempted proofs of this conjecture, I try to look at some special choices of these disjointifying sets and so on, in such a way that will give you a tree. Well, it didn't work. Otherwise, I would ring all the bells. Okay. So now let's, for the few minutes that I'm left, let me say something about survival of these properties under forcing extensions. small forcing extensions. The compactness. Again, a decent large cardinal thing, we assume that until 12, right? So now if you think about, for instance, a stationary reflection, a successor of singular, if you do forcing less than the singular, definitely that preserves stationary reflection. Every new stationary set contains an old stationary set, if every stationary reflect, you can reflect it to a point of high enough cofinality that if every stationary set reflects, that it's not affected by the small forcing. What about the tree property? So now again, something emerges which may indicate the difference between Aleph Omega and Aleph Omega square. Now, a result together with ℵω2 shows that assuming the consistency of omega many supercompact cardinals, then you can have a situation in which a model in which Aleph Omega plus 1 has the tree property, but if we simply collapse omega 1, we do the Levy collapse of omega 1, then you lost the tree property. And you lost the tree property in the strongest sense, namely that there exists a special Einstein tree on Aleph Omega plus 1. The point is that you essentially get something which is almost a weak square, except that you missed some small enough points and then of small cofinality, and then the collapse, if collapse omega 1 to omega, then you exactly completed the weak square. And that's very likely true in every model in which Aleph Omega plus 1 is true. I don't know that. But unfortunately, we thought maybe we could show that for Aleph Omega plus 1, every model in which the tree property holds, you can destroy it by doing small forcing. Something that may indicate that may be not the case, that it is consistent, that it has the tree property, and the tree property is preserved under small forcing, again typo, of size less than Aleph Omega, by any sigma closed forcing. Then with sigma closed forcing, it's consistent that it survives the thing. But Aleph Omega square plus 1 can be resilient to, the tree property can be resilient to any small forcing. Again, typo. Assuming the consistency of omega many supercompact cardinals, it is consistent to have a model in which Aleph Omega square plus 1 is the tree property, and it preserves the tree property under any forcing extension by forcing of cardinality less than, it should be Aleph Omega square. The plus 1 is a typo there. And of course, you can't have it for a thing of size Aleph Omega square, because you can collapse it to omega. Now, Aleph Omega square plus 1 will become Aleph 1. Aleph 1 fails the tree property automatically. This is Arenstein result. Okay, so again, it's something that we don't know definitely, but it smells that there is a fundamental difference between Aleph Omega and Aleph Omega square. So if we take the conclusion of our listed properties of Aleph Omega plus 1 can consistently have only the tree property, limited Chang conjecture, and stationary reflection. The Chang conjecture and stationary reflection, it can have both. Assuming the consistency of one supercompact, then it is consistent, then, I'm sorry, it can have the tree property and the Chang conjecture. That's not, I'm sorry, not the consistency of one supercompact, omega many supercompact for the tree property. But it cannot have simultaneously stationary set reflection with the Chang conjecture. On the other end, Aleph Omega square plus 1 can have consistently have all the compactness properties simultaneously, and much more than I listed. So there is a fundamental difference between Aleph Omega square and Aleph Omega. Aleph Omega square plus 1 is very different from Aleph Omega plus 1. Dear you and Ted, thank you for the wonderful mathematics, but also thanks for making the Singapore Logic Summer Program being the great success it is. Thank you. Sorry? Aleph Omega plus omega is bad. I mean, it's not true that the cardinals up to Aleph Omega square are bad. They are roughly they're as bad as Aleph Omega. Well, for instance, it's not true that, that you got a fixed cofinality such that every scale of that cofinality is good. But there is a notion of semi-good, which the scales on Aleph Omega plus Omega from then on are semi-good, up to Aleph Omega square. And by the way, there is a funny thing going on, because, okay, you know that Aleph Omega square plus 1 can be good. What about cardinals past Aleph Omega square plus 1? They can be good for a while. But where is the first point you get into trouble? Aleph Omega 1. At Aleph Omega 1, you get into trouble. Definitely, there is a ZFC counterexamples to compactness. And it's not even known whether you could have consistently, whether you can have the compactness phenomenon, delta reflection, say, through the whole interval between Aleph Omega square and Aleph Omega 1. The difficulty of getting the consistency of that is very similar to getting the consistency of the singular cardinal hypothesis, Aleph Omega being strong limit, and 2 to Aleph Omega being above Aleph Omega 1. It's the same type of obstacles to the forcing proof, the consistency proof.
Continuing on that line, does anything change Aleph Omega 2?
No. The first point where you can have full from then on, all the compactness properties I'm talking about will be true. I'm not talking about the tree property, which I'll say in a sentence in a minute, but it's the first cardinal fixed point. It's the first alpha. From then on, you could have the delta reflection property from then on. The tree property is a problem, because I think one of the most interesting problems about the tree property is, for instance, can the tree property be consistently true for all regular cardinals above Aleph 1? We know that Aleph 1 cannot have the tree property. Is it consistent from then on? That's not known. And there is a game of trying to push for larger and larger interval gain in the tree property. The best, what would you say the best? Yair got it up to Aleph Omega square. Spencer Unger, no, I think Yair is the...
Yeah, we did those things in San Jose.
Yeah. So right now, the official record is all regular cardinals, except Aleph 1, of course, up to Aleph Omega square. Yeah.
Can we distinguish between the system hypothesis and the tree property?
No, not that I know. You know, I find it also difficult, James. This is something we looked at some point. Even getting, for instance, no Suslin tree, but still having an Argentine tree. That's.